visible. Not because it's far away or hidden, but because it's simply too small to see. Imagine, right now, there are entire universes living on your skin, floating in the air, and buzzing inside your own body. But for thousands of years, people had no idea. All they knew was what their eyes could show them. If you couldn't see it, it practically didn't exist. So, where did all our modern knowledge begin? With one simple invention, the microscope. Someone, somewhere, asked, "What if I could see things smaller than my eyes allow?" That tiny question changed everything. With the first microscopes, scientists suddenly found a brand new world: cells, bacteria, and even the building blocks of life. The rules of medicine, biology, even physics, shifted overnight. Every leap forward in science in some way connects back to how much deeper we learn to see. The microscope evolved, from rough glass lenses in the 1500s, to today's powerful instruments that can reveal the very atoms that make up our world. Each step revealed a new layer of reality, and forced us to rethink everything we thought we knew. So, this isn't just the story of a tool. It's the story of how curiosity, a bit of glass, and the drive to see more, completely changed what it means to understand the world. Let's dive in, right to where it all began.
Welcome to For Science Salah Lotfy channel, where global scientific research becomes clear and accessible.
هنا نحول الأبحاث العلمية العالمية إلى معرفة مبسطة مترجمة لك بلغتك.
Ici, la science est expliquée et traduite pour tous.
Ciencia clara, accesible y disponible en varios idiomas.
Wissenschaft, verständlich und mehrsprachig für jeden.
قناة For Science Salah Lotfy Channel. العلم للجميع وبجميع اللغات. تابعنا لاكتشاف المزيد.
The story of the microscope begins with a simple question: what lies beyond the limits of our sight? At the end of the 16th century, Europe was changing rapidly, glassmaking was improving, lenses were becoming clearer, and, honestly, curiosity about the natural world was growing. Around the year 1590, two Dutch lens makers, Hans Janssen and his son Zacharias, combined multiple lenses inside a tube. What they created was simple, but, revolutionary: the first compound microscope. It could magnify objects only a few times, about 3 to 9 times their real size. By today's standards, this was extremely limited. The images were blurry, distorted, and poorly lit, yet for the first time in history, humans could see details smaller than the naked eye could ever detect. But the real breakthrough did not come from complex instruments. It came from one man, and, well, just one lens. Antony van Leeuwenhoek, a Dutch tradesman with no formal scientific education, learned how to grind glass better than anyone else of his time. Instead of using many lenses, he perfected single-lens microscopes with extraordinary clarity. When Leeuwenhoek looked at drops of water, dental plaque, and blood, he saw something no human had ever seen before. He saw living organisms, tiny, moving forms of life. Bacteria, protozoa, microscopic life everywhere. This discovery shattered the belief that life only existed at scales visible to the human eye. Leeuwenhoek carefully documented his observations and sent them to the Royal Society in London. At first, many scientists doubted him. What he described sounded unbelievable. But once confirmed, science was changed forever. For this reason, Leeuwenhoek is often called the father of microbiology. Shortly after, in 1625,
by the early 19th century, microscopes were not exactly a new invention. They had been around for quite a while, letting curious people peek into a world hidden from the naked eye. Scientists and wealthy hobbyists alike had these instruments in their studies, marveling at the intricate details of a fly's wing or the tiny creatures swimming in a drop of pond water. It was, honestly, a fascinating time, a bit like having a secret window into another universe. These early microscopes were quite good at one thing: making small things look much, much bigger. You could take something impossibly tiny and magnify it hundreds of times, which was, of course, terribly exciting. The problem was that making things bigger didn't automatically make them clearer. In fact, it often made things worse. Imagine looking at a newspaper through a very cheap magnifying glass. The letters get bigger, yes, but their edges become fuzzy and smeared with strange colors. This was precisely the trouble early microscopists faced. They would crank up the magnification, hoping to see the secrets of life, only to be met with a frustrating, blurry mess. The more powerful the lens, the more distorted the image became. It was a significant roadblock for science, leaving researchers to wonder if what they were seeing was real or just a flaw in the glass. This distortion was caused by some rather inconvenient facts of physics. The main culprits were two troublemakers called chromatic and spherical aberration. Chromatic aberration happened because a simple lens acts like a prism. When white light passes through it, the lens splits the light into its rainbow of colors. Each color bends at a slightly different angle, so they don't all focus at the same point. This created annoying color fringes around everything you looked at, making a clear view impossible. It was like trying to read a book where every letter was outlined in a blurry rainbow, a constant distraction that obscured the true details of the object. Spherical aberration was another headache altogether. This problem came from the very shape of the lens itself. Lenses were typically ground with a spherical curve, which was the easiest shape to make. Unfortunately, light rays hitting the edge of a spherical lens are bent more sharply than those hitting the center. This means that, once again, the light doesn't focus to a single sharp point. The result was an image that was clear in the very middle, but grew progressively fuzzier and more distorted toward the edges. For scientists trying to make accurate drawings of cells or bacteria, this was a disaster. Their observations were unreliable, and progress in biology was held back by these fundamental optical flaws. For science to move forward, someone had to figure out how to build a better lens. The challenge was immense, requiring a deep understanding of both glassmaking and the physics of light. The big breakthrough came from a clever idea. What if you could cancel out the errors of one lens by using another? This led to the development of the achromatic lens. The concept was wonderfully elegant. It involved sandwiching two different types of glass together, typically a convex crown glass lens and a concave flint glass lens. Each type of glass bent light in a slightly different way, with different refractive properties. The magic happened when they were combined. The crown glass would split the light into its colors, just as before. But then, the flint glass would bend the light in the opposite direction, pulling those scattered colors back together. It was a bit like having two prisms, one that creates a rainbow and a second that neatly reassembles it back into white light. The result was a compound lens that could focus different colors of light to a single point. Suddenly, the distracting and misleading color fringes that had plagued microscopy for over a century simply vanished. The image became crisp and true to life, without the colorful halos. This invention, perfected by brilliant minds like Joseph Jackson Lister, the father of the famous surgeon, completely transformed the world of microscopy. With chromatic aberration solved, scientists could finally trust what they were seeing through the eyepiece. A cell was no longer a blurry blob with a rainbow edge. It was a distinct object with a clear boundary and visible internal structures. This was a monumental leap. Observations that were once speculative or debatable became verifiable facts. Scientists could now confidently identify and classify microorganisms, study the structure of tissues, and watch cells divide with newfound clarity. The impact on biology and medicine was immediate and profound. With clear, high-resolution images, the German botanist Matthias Schleiden could propose that all plants were made of cells, and his compatriot Theodor Schwann could extend that idea to animals, giving birth to modern cell theory. Doctors and researchers could finally see the bacteria responsible for diseases like cholera and tuberculosis, leading to a revolution in public health and a deeper understanding of how illnesses spread. The achromatic lens didn't just improve an existing tool. It unlocked a new era of scientific discovery, turning the microscope into a reliable instrument of truth. As wonderful as the new achromatic microscopes were, they still had one limitation that was inherent in their design. They showed the world in only 2 dimensions. When you looked through a standard microscope, you saw a flat image. Everything was squashed onto a single plane, so you could see length and width, but you lost all sense of depth. This was perfectly fine for looking at very thin slices of tissue, but it was less helpful for examining the surfaces of larger, more complex objects like insects, crystals, or the delicate parts of a flower. You couldn't appreciate their three-dimensional structure. To solve this problem, another ingenious invention was needed, the stereo microscope. The idea was pioneered by several individuals, but it was the American biologist and instrument maker Horatio S. Greenough who designed the first truly practical version in the late 19th century. His design was based on a simple but brilliant principle that mimicked human vision. We see in 3 dimensions because our 2 eyes look at the world from slightly different angles. Our brain then merges these 2 slightly different images into a single 3-dimensional perception, a process known as stereopsis. Greenough's stereo microscope did exactly the same thing. It was essentially 2 separate microscopes mounted side by side, each with its own objective lens and eyepiece, both angled slightly to converge on the same specimen. The left eye looked through the left microscope, and the right eye looked through the right one. Each eye received a slightly different perspective of the object under observation. When the user looked through the binocular eyepieces, their brain fused these 2 separate images, creating a stunning and incredibly useful 3-dimensional view. The effect was immediate and powerful. The importance of this cannot be overstated, especially for fields that require delicate manipulation of small objects. Biologists could now dissect tiny organisms with greater precision because they could perceive depth. Geologists could examine the surface texture of minerals and fossils in glorious 3 dimensions. Watchmakers, jewelers, and industrial engineers also found the stereo microscope to be an indispensable tool for working with small, intricate parts. It wasn't just about seeing things, it was about interacting with them. The stereo microscope provided the spatial awareness needed to perform tasks that would have been impossible with a traditional 2-dimensional view. By the end of the 19th century, the microscope had become a truly remarkable instrument. Thanks to the invention of achromatic lenses and other optical corrections, microscopists had essentially achieved a perfect lens system. They had conquered the frustrating distortions of chromatic and spherical aberration. The images they could produce were incredibly sharp, clear, and free of artifacts. The stereo microscope had even added the dimension of depth to their observations. It seemed as though there were no more optical problems left to solve. Scientists could now build microscopes with higher and higher magnification, confident that the image quality would hold up. However, as they pushed the limits of magnification, they ran into a new and far more fundamental barrier, one that couldn't be fixed by grinding a better piece of glass. This limit was imposed by the very nature of light itself. Light travels in waves, and like any wave, it has a wavelength. It turns out that you cannot use light to see details that are smaller than about half of its wavelength. Think of it like trying to measure the thickness of a single hair with a standard ruler marked only in inches. The tool is simply too coarse for the job you're trying to do. This physical law, first described by the German physicist Ernst Abbe, is known as the diffraction limit. It meant that no matter how perfect your lenses were, there was a point beyond which you simply couldn't resolve any more detail using a conventional light microscope. For visible light, this limit is around 200 nanometers. You could magnify an image 1,000,000 times, but it wouldn't reveal any new information. You would just get a bigger blur. This was a hard physical boundary, an invisible wall that microscopy had finally run up against after a century of incredible progress. So, as the 19th century drew to a close, the field of microscopy found itself at a crossroads. The revolution in lens design had taken science to the very edge of what was possible with light. It had revealed the world of cells and bacteria, fundamentally changing our understanding of life. But to see even smaller things, to peer inside a bacterium, or to see a virus for the first time, would require a completely new way of thinking. The stage was set for the next great leap, one that would have to abandon light altogether and harness a new kind of illumination to break through the diffraction limit and venture into the truly unseen world.
Imagine staring into a world that's completely invisible to the naked eye. Back in the early 20th century, scientists hit a brick wall, literally. No matter how powerful their microscopes got, there was a hard limit. Why? Because of light itself. Light waves could only reveal so much, and anything smaller than about 200 nanometers, think viruses or the detailed machinery inside your cells, was totally out of reach. So what did scientists do? They asked a question that changed everything. What if we stopped using light altogether? Enter 1931, and a young German physicist named Ernst Ruska. This guy had a bold idea. Instead of light, he used electrons, tiny particles that, believe it or not, have wavelengths thousands of times smaller than visible light. The result? The very first transmission electron microscope, or TEM. Suddenly, the rules changed. With electrons shooting through ultra-thin samples, scientists could peer into the nano-world. Viruses, now visible, the tiny engines inside cells, clear as day, materials once thought solid and featureless, they revealed intricate, hidden architecture. It was like discovering a new continent, except this time, the landscape was measured in billionths of a meter. But the story doesn't end there. Soon, another leap, the scanning electron microscope, or SEM. Instead of looking through things, SEM scanned their surfaces with a focused beam of electrons. The images? Absolutely stunning. Sharp, detailed, almost three-dimensional. Imagine seeing the surface of a fly's eye, or the texture of metal, blown up thousands of times. Things you'd never dream of seeing suddenly looked like alien planets. And then, in 1981, science took a quantum leap, literally. That's when the Scanning Tunneling Microscope, or STM, appeared on the scene. This was next level. It didn't just show the shapes of molecules, it mapped individual atoms using a quantum effect called tunneling. For the first time in history, atoms weren't just theoretical, they were real, visible, and even touchable in a way. This was the moment nanotechnology was born. So, why does this matter? Because every leap in microscopy has unlocked entire new fields of science. We've gone from seeing the outlines of cells, to peering inside them, to rearranging atoms themselves. The electron microscope didn't just break the rules, it rewrote them. And just when you thought the story was over, light is about to make an unexpected comeback. But that's a story for another time.
Exposing the myth in microscopy. What if I told you we can now see things smaller than what light should allow? You need to watch this if you've ever wondered how science turns the impossible into reality. For over a century, scientists believed light set a hard limit on what we could see under a microscope. Anything smaller than about 200 nanometers just turned into a blur, no matter how powerful the lens. It felt like a dead end, but science thrives on breaking boundaries. In the 1990s, researchers realized maybe it's not about stronger lenses, but smarter ways of using light. Enter super-resolution microscopy. One breakthrough called STED, stimulated emission depletion, was a total game-changer. By cleverly turning light off around a tiny spot, scientists could see details way below the so-called limit. Suddenly, the impossible became possible. Techniques like Palm and Storm pushed things even further. They tracked single glowing molecules, one blink at a time, to build up ultra-detailed pictures, molecule by molecule. The results? We can now watch proteins moving inside living cells, see how molecules interact in real time, even catch life's tiniest dramas as they unfold. This revolution earned a Nobel Prize in 2014. And with smart cameras and AI, microscopes today are more like digital windows into the invisible world. Breaking the light barrier wasn't the end, it's just the beginning. So, where will we look next?
They say seeing is believing, but what if we could see far beyond belief itself? For centuries, Microscopes have unlocked the hidden universe, revealing everything from bustling cells to the secrets of viruses. But today's microscopes are more than just glass and lenses. They're supercharged by artificial intelligence and connected across sciences. Imagine machines that scan thousands of samples on their own, or AI that deciphers images faster than any human eye. This technology is already transforming medicine, catching diseases earlier, making treatments personal. In materials science, it means stronger, lighter, smarter inventions. In nanotech, it's like playing chess with atoms, moving them, building the future molecule by molecule. But here's the real wonder. The best is yet to come. Soon, we might watch molecules dance in real time inside living bodies, or combine multiple imaging powers into one tool, revealing mysteries we haven't even dreamed of. Every leap in vision makes the world bigger and our questions deeper. The story of microscopy is proof. Curiosity plus clarity equals progress. So, what's the next frontier? As long as we ask, what's beyond what we see? The microscope will keep evolving. Because the invisible isn't empty, it's full of discoveries, waiting for us to look closer.
As we reach the end of this episode, one message becomes clear. No scientific device appears suddenly. Behind every instrument we use today lies a long journey, an idea refined, a concept challenged, an experiment repeated countless times. The microscope is only one example, but its story reminds us that every scientific tool, in medicine, physics, chemistry, engineering and beyond, is the result of centuries of human effort. Each improvement came from someone who asked a better question. Each breakthrough was built on the work of those who came before. Progress in science is never the achievement of one era or one mind. It is a continuous chain of knowledge passed across generations. Understanding how an idea evolves, how an instrument is developed, and how science advances step by step helps us truly appreciate the tools we rely on today. So here at For Science Salah Lotfy channel, we pause to express sincere respect and gratitude to the scientists, engineers and thinkers who devoted their lives to expanding human vision, literally and intellectually. And finally, I would like to thank you, the viewers, for your time, your curiosity and your interest in science. I invite you to share your thoughts in the comments on the For Science Salah Lotfy channel. Your perspective matters and your questions keep this scientific dialogue alive. I am Professor Dr. Salah Lotfy, professor at the Egyptian Atomic Energy Authority. Thank you for watching.